Let's start solving some inequalities. Inequalities are statements that indicate that one expression is less than, greater than, less than or equal to, greater than or equal to another expression. In this video, we're going to focus on linear inequalities and absolute value inequalities. A linear inequality is an inequality where the highest power of the variable is 1. So kind of like a linear equation, but with an inequality symbol instead of an equal sign. Our process is going to be similar as well. We're going to isolate the variable on one side, but there's going to be one hitch. If we need to multiply or divide both sides of the inequality by a negative number at any point, we need to flip the direction of the inequality in order to keep the statement equivalent to what we started with. So I'll demonstrate that issue here. In this example here, we have negative 3x plus 7 is greater than or equal to 25. I want to isolate the variable term, so I'm going to subtract 7 from both sides and get negative 3x is greater than or equal to 18. And now we need to divide both sides by negative 3. And when we divide by negative 3, we have to flip the direction of the inequality. So I'm going to write this as a completely separate step. I'm going to divide the left side by negative 3. I'm going to divide the right side by negative 3. And in order to keep this equivalent to the previous line, I have to flip the direction of the inequality. Now I carry out the step, and I get that x is less than or equal to negative 6. Now what are we saying with this answer? We're saying that any number less than or equal to negative 6 will make this statement true, and numbers that are bigger than negative 6 will make the statement false. So we can't check this in the same way that you can check an equation because there are too many inputs to check. We have infinitely many answers here, infinitely many solutions. But we might pick one or two and see if they make the statement true. Let's start with negative 6. Our statement claims that if we plugged in negative 6, it would make the statement true. Negative 3 times negative 6 is 18. 18 plus 7 is 25. 25 is equal to 25. When we say greater than or equal to, we're saying one of those conditions has to be met. You can't possibly meet both at the same time. So negative 6 makes the statement true. It is a solution. It claims if we pick any number less than negative 6, it will make the statement true. Let's try another one, like negative 8. Negative 3 times negative 8 is 24, and 24 plus 7 is bigger than 25. It turns out to be 31, but it doesn't matter what it comes out to. It just matters that it's bigger than 25. If we picked a number bigger than negative 6, it won't work, like 0. If I plug in 0, negative 3 times 0 is 0, and 0 plus 7 is only 7. That's not bigger than 25. So this simultaneously tells us which numbers work and which numbers don't work. Now it's kind of standard to write our final answer in what we call interval notation. And here are some pictures to remind you of the interval notation for various subsets of the number line. If you're going between two bounds A and B, then the lower number goes on the left and the bigger number goes on the right. And if the endpoint is included, we use a square bracket. If it's excluded, we use a parenthesis. We call this first interval an open interval because neither of the endpoints are included. The second interval is called a closed interval because both of the endpoints are included. The other two are half open because only one side is included. If you only have an upper bound, then we use negative infinity on the left side of the interval notation. And the negative infinity would always get a parenthesis because it's not a number, it's a way of expressing unboundedness. So you can't include it on the interval in this context. Whether or not the upper bound is included determines whether you put a parenthesis or a bracket. If there's no upper bound, then we use a positive infinity on the right, and I don't tend to write the plus on it, I just write infinity. The lower bound here is A, and again, excluded with a parenthesis, included with a bracket. If the answer can be any real number at all, the interval notation for that is the interval from negative infinity to infinity. Again, parentheses on both. We're using infinity here as a way of expressing unboundedness, not as a number, so don't try to include it on your interval. Some of you might be familiar with the set notation for this, the boldface R. That's the same thing. But in interval notation, we write it like this. Back to our example. We're saying that x is less than or equal to negative 6. What would the interval notation for that be? If you're comfortable with interval notation, you can just write it down. If you're not sure, draw the number line graph and see what it would look like. If x is less than or equal to negative 6, then we're considering numbers to the left of negative 6 as well as negative 6 itself because of the equality. Now you can see we've got no lower bound. And so we use minus infinity on the left side to indicate that. Our upper bound is negative 6, and that negative 6 is included because of the or equal to part of our inequality. The end of our algebra steps represent the inequality version of our solution. This is the interval notation version of our solution. And again, I want you to get it comfortable with this because it gets used a lot, especially at levels past this one. Let's look at what we call a compound linear inequality. This is compound because we're considering two inequalities. We're saying that -3 is less than or equal to 5x minus 2 over 4, and 5x minus 2 over 4 is less than or equal to 2. So we call this a compound inequality. It's a linear inequality because the variable is only raised to the first power. How would we solve an inequality like this? Well, I encourage you to consider what you would do if this part was missing. If the second inequality symbol was missing, you'd probably multiply by 4 to get rid of the fraction. What if the left side was missing? You'd probably multiply by 4 to get rid of the fraction. So let's just multiply all three parts by 4. When you're solving an inequality of this type without breaking it into cases, whatever you do to one part of the inequality, you have to do to the other two parts. Now here we're multiplying by a positive number, so we do not have to change the direction of the inequalities. And now we play the same game. What would you do if the second inequality wasn't there? Well, you'd probably add 2 to isolate the variable term. And what would you do if this left side was missing? You'd probably add 2. Let's just add 2 everywhere. How do we finish this off? Well, we divide by 5. We just make sure to divide by 5 everywhere. We're dividing by a positive number, so no need to flip the direction of the inequalities here. And now we see that x is bounded by 2 numbers. This is an example of the left side here, where we're bounded between 2 numbers. If we draw the picture for this, our left bound would be -2, our right bound would be 2. And we're considering all of the numbers between those two as well as the bounds themselves. So the interval notation for this would be the interval from -2 to 2 inclusive. When we say inclusive, that means including both bounds. Let me get rid of my first step here and we'll just check a number on this interval. Like 1 lives on this interval. 1 is between -2 and 2. If I plug 1 in for x, the numerator becomes 3 and we get 3/4, which really is between -3 and 2. It works. Let me pick a number that's not on the interval, like 3. 3 is too big to be on the interval. 5 times 3 is 15. 15 minus 2 is 13. 13 divided by 4 is bigger than 3. It's 3.25. When we plug in 3, we do not get a number that's between -3 and 2, and therefore it's not a solution. Again, we can't possibly check all solutions one at a time because there are infinitely many. But you might consider checking a number that's on the interval and checking a number or two that's off the interval and making sure that the solutions work and the non-solutions don't. So these linear inequalities are pretty straightforward. The one thing you have to remember is that if you multiply or divide both sides by a negative number, you have to flip the direction of the inequality. Let's move on to absolute value inequalities, and we'll get more practice with the linear ones as we do these. To solve absolute value inequalities, we're going to isolate the absolute value expression on one side and then consider cases. Just like with absolute value equations, we have to consider cases with absolute value inequalities. In our first example here, we're looking at the absolute value of 3x plus 5 is greater than 10. The absolute value expression has already been isolated on one side, and now we have to consider the cases. When would the absolute value of a number be bigger than 10? Well, let me do this on another slide. Like I've done in the past, I'm going to use u as a replacement for our expression and ask when does the absolute value of a number, which I'm representing by u here, be bigger than 10? Let me put this on a number line and see. Remember that the absolute value of a number is just its distance from 0. So when would the distance from 0 be more than 10? Well, if you're to the right of positive 10, then the absolute value of your number is bigger than 10. Notice that I don't want to include 10 because the absolute value of 10 is not bigger than 10. There's another case though. What if we were on the other side? We could also go more than 10 units to the left of 0. So starting to the left of -10. Not including -10. So it looks like there are two possibilities here. Either our number is less than -10 or our number is greater than 10. But that splits that into two cases that don't have the absolute value bars, and then we could proceed from there. We're going to do the same thing in our example. There are two possibilities. Either our expression 3x plus 5 is less than -10, because if 3x plus 5 is less than -10, its absolute value will be bigger than 10. It'll be more than 10 units away from 0. Or 3x plus 5 could be bigger than 10. That gives us two linear inequalities. The steps to solving each are the same, so we're going to do these simultaneously. I can subtract 5 from both sides to isolate the linear term. We get 3x is less than negative 15, or 3x is greater than 5. We divide both sides by positive 3. That does not require us to flip the direction of the inequality. We get that x is less than negative 5, or x is greater than 5/3. You can flip back to the picture of the intervals if you need to. I'm just going to write these out on the screen. If x is less than negative 5, that means we're on the interval from negative infinity to negative 5, not including negative 5. An inequality like this is called a strict inequality. In a strict inequality, we do not include the bound. The interval on the right would be the set of numbers greater than 5/3, so not including 5/3. Don't include it, up to positive infinity. And then rather than writing the word or, which I think is acceptable, the math symbol that we use here is called a cup, but it looks like a U. We read this as union. So this is the union of these two intervals, the union of the interval from negative infinity to negative 5 and the interval from 5/3 to infinity. Again, it's technically called a cup. Most people just call it the U because it kind of looks like a U. What we're saying here at the end is you can either pick a number that's less than negative 5 or greater than 5/3 and it will make the statement true. If you pick a number between those, it won't work. Again, let me bore you just to make sure. If I pick negative 6, 3 times negative 6 is negative 18. Negative 18 plus 5 is negative 13, but its absolute value would be 13, which is bigger than 10. So the candidate that we chose on this interval worked. That doesn't guarantee that our interval is right, but if it didn't work, we'd know we were wrong. 5/3, that's a little bit smaller than 2, so let's test 2. 2 should work. 3 times 2 is 6, 6 plus 5 is 11. The absolute value of 11 is bigger than 10. Good. If we pick a number in between, it should not work. 0 is an obvious choice. 0 plus 5 is only 5, and the absolute value of 5 is not bigger than 10. So let's go back through our logic. Here the absolute value expression was already isolated, so we could start by splitting it into cases. I considered what it means for the absolute value of a number to be greater than 10, thought about what cases would satisfy that, and then just did the same thing with our more complicated expression. We solved the two linear inequalities that resulted from that, recognizing that one or the other has to be true, and we found the interval notation for each and took the union of those two intervals as our solution. Let's do another simple example where the absolute value bars are already isolated. This time we'll consider a less than or equal to example. This says the absolute value of x minus 4 is less than or equal to 0.001, or 1/1000th. That's the nerdy way to read that. I know that seems like a strange number to have on the right, but inequalities like this are actually very common. They're used for tolerance when there's a certain amount of error that's involved. Basically, this inequality is saying that the value of x must be within 1/1000th of 4. So maybe you're making measurements of some type and your measurement can only be off by 1/1000th. That's the tolerance. So inequalities like this are actually fairly common. I want to break this one into its cases as well because the absolute value bars are already isolated. Let's consider what it means for the absolute value of a number to be less than or equal to 0.001. Well, that means that your distance from 0 is within 1/1000th. So 0 lives here. We could be as far away as positive 1/1000th or as far away as negative 1/1000th. We want our distance to be less than or equal to that. So now we want the numbers in between those two bounds. So we get another one of those compound inequalities. We know that the value of u has to be between negative 1/1000th and positive 1/1000th. Well, let me just apply that to our expression x minus 4. X minus 4 must live between negative 1/1000th and positive 1/1000th. To solve that inequality, we just ask what we would do to get x alone and then apply that to all three sides of the inequality. We would add 4 to isolate the x. On the left, negative 1/1000th plus 4 is 3.999, 3 and 999 thousandths. X is isolated in the middle. On the right, when we add 4, we get 4 and 1/1000th. If you think about it, those two bounds are exactly 1/1000th away from 4. And and we're saying that x has to be within that range, including the bounds. So going back to our tolerance explanation of what this interval says, if you were making some machine part that had to be 4 millimeters long and your tolerance was only 1/1000th of a millimeter, then you'd have to be between 3.999 millimeters and 4.001 millimeters, and that's basically all this says. The interval notation for this we've already seen because we're going between two bounds. We're going to start at 3.999, and we're going to end at 4.001. Why don't we need a union here? Because we're going between two bounds. In the previous picture where we're going outside of two bounds, we had two intervals that did not overlap. We call them disjoint. Our intervals were disjoint. We couldn't consolidate them into a single interval. Here we only have a single interval, and so we can get away with a single set of brackets. Okay, let's look at a couple where we have to isolate the absolute value bars. So this says 5 times the absolute value of x minus 4 plus 6 is less than 41. Think of this absolute value expression as a singleton variable. How would you isolate it? Well, I think most of us would start by subtracting 6. So we get 5 times the absolute value expression is strictly less than 35. Then we divide both sides by 5. And we get the absolute value of x minus 4 is strictly less than 7. I know I wasn't very imaginative here because I used another x minus 4. But maybe it's good that I was repetitive here, because what I actually want you to do is go back to the previous problem and see if you can rewrite this without absolute value bars. Consider cases. Pause the video and see if you can come up with it. Because the absolute value of x minus 4 has to be less than a positive number, we're going to sandwich between the two. It's just like the previous example, except the number on the right is 7 instead of 1/1000th. And we have a strict inequality this time, but that doesn't change our rules. To get the x alone, you add 4 to all the sides, and we get that negative 3 is strictly less than x, which in turn is strictly less than 11. See if you can write that in interval notation. Because we're going between two bounds, we're going to have a lower bound of negative 3 and an upper bound of 11. And to indicate that we don't want to include the bounds, we use parentheses. So any number between negative 3 and 11 will make that statement true. Any number outside of that interval, including the bounds themselves, will make the statement false. If you plug one of those bounds in, you'll get 41 on the left side, and 41 is not less than itself. The hardest part, of course, is going from the step where you have the absolute value bars to the step where you do not. I like to think of it in terms of these pictures, but there's actually a set of rules that apply, and I've written them here so that you can copy them down if you want. When d is a positive number, if the absolute value of x is less than d, then you sandwich x between minus d and d. You can think of that as a rule. I don't like to think of it as a rule. I think of it as a picture. I can't memorize all of these rules. I used to memorize a bunch of rules, but I've run out of room for that stuff. My brain's too clogged up with 90s music lyrics and commercial jingles and stuff. I don't have any room for anything anymore. I'm lucky when I can remember my kids' names. So I can't memorize all of these rules. So I just think of it in terms of what everything means. I have to memorize definitions. You can't get around that. But once I've got the definition, from there you can use logic to come up with these rules. This statement means that the distance has to be less than d units, so I'm between minus d and d. Okay, I get it. Notice that that rule only works if d is positive. I'll talk about that in a moment. Before we do that, let's do one more example. This one says negative 3 times the absolute value of the binomial 2x plus 6 plus 20 is less than or equal to 8. Pause the video and see if you can get those absolute value bars isolated. Don't forget to account for this negative number out front. Okay, so I would subtract 20 from both sides, leaving negative 3 times the absolute value of 2x plus 6 is less than or equal to negative 12. And now I'm going to divide everything by negative 3. And I like to do this as a separate step. So I'm going to divide by negative 3 here, and I'm going to divide by negative 3 here, and then write greater than or equal to. You might wonder why I don't just divide the previous line by negative 3. Well, technically that's incorrect, because when I divide by negative 3 there, this should be flipped. So that you can see my work, I want to write all those steps out. You're welcome to abuse notation like that and divide by negative 3 here and then flip the symbol in the next step, but I can't do that. It would bother me. So I get the absolute value of 2x plus 6 is greater than or equal to 4. See if you can split this into cases. If you want to go back to the previous example, that's fine. Or you can use our rules. Let me flash them here. We're looking at the first rule this time. But see if you can split this into cases. Okay, if the absolute value of 2x plus 6 is greater than or equal to 4, then there are two possibilities. Either 2x plus 6 is less than or equal to negative 4, or 2x plus 6 is greater than or equal to 4. The way that a lot of people like to memorize this is one of the inequalities is exactly the same as what you started with, but with the absolute value bars gone. In the other inequality, you flip the direction of the inequality and you change the sign on the number. I haven't given myself a whole lot of space here, so let me do this without showing the steps. I'm going to subtract 6 from both sides in each. I divide both sides by positive 2, which does not require me to flip anything. And now we get two cases. X can be less than or equal to negative 5, which is the interval from negative infinity to negative 5, including negative 5, because of the or equal to part. Union, instead of writing or, we use the set notation, union. And then the other possibility is that x is greater than or equal to negative 1. Well, that would be the interval from negative 1 to infinity. Notice that the negative 1 has a bracket on it because we can include it. Infinity and negative infinity never get brackets. We're not plugging those in as numbers, so you can't include them. Again, here are those rules if you want to memorize them. I prefer to just ask myself what the expression means, but it's completely up to you how you do it. Now, one important part of this rule is that the number on the right has to be greater than 0. If the number on the right is not positive, you're still considering cases, but the cases won't be this. It's a special case. Let me give you an example. This one says the absolute value of 12x plus 7 is greater than negative 2. Don't start by going back to our rules. Our rules don't apply because d is not greater than 0 here. The number on the right is negative. This is asking, when would the absolute value of this expression be greater than negative 2? Well, we know that the absolute value of a number is always greater than or equal to 0, so it's certainly always going to be greater than negative 2. This is a special case, or what some students would call a trick question. This is always true. Doesn't matter what value of x you plug in, this will always be true. Every real number makes this true. There's no work to be shown here. It's just the set of all real numbers. You can pick any real number you want, and when you plug it in there, it will make the statement true. Here's another special case. It says the absolute value of 4x minus 23 is less than 0. That means that the absolute value of that expression on the left is negative. Well, that can't happen. This never happens. The absolute value of a number is never less than 0. This has no solution. Now, some textbooks will spring this kind of thing on you, so I guess I should throw this in real quick. What if it had said less than or equal to? Well, I consider cases. Either the absolute value of 4x minus 23 is less than 0, or the absolute value of 4x minus 23 is equal to 0. Now, we just said this can't happen, but over here this could happen. If 4x minus 23 was equal to 0, this would happen. So this is a weird situation where an inequality has only one solution. There's one number that makes this true because we're allowing for the expression to be equal to 0. The equation has a solution where the strict inequality does not. Now we're really pushing the edges of what we might see. I really just wanted to cover the first one, but then it struck me that maybe I should bring that up. Unless you wind up with a future instructor who's really not nice, you won't see these special cases very often. You'll much more commonly see the examples that require these rules or the thought process that I use where I draw the picture. That's what I'd like you to focus on. As always, if you have any questions for me on the lecture or what you need to focus on, shoot me an email. See me in an office hour.